Hi there, today is the 21st of June and I'm starting my video series on Chapter 7 in which we're going to be talking about the elements of risk. Okay, back in our very first chapter we talked about the 5 principles of finance as I was best able to define them for you, and risk and return always went together. That's a key element, that's an underpinning of anything that you do in the study of finance. Okay, I know of really no exceptions to that. Okay. So if you take on more risk, you expect more return, and if you want more return, you have to take on more risk in general. Okay, so let me blow this up for you. Now, if risk is so important to us as investors, we want to make sure that we have a way of measuring the elements that make it up. They do exist. It's not just a matter of rolling the dice or going to Foxwoods, okay? So, I want you to remember throughout this chapter that people are inherently risk averse. Human beings are risk averse. We seek comfort, we seek shelter, we seek safety, okay? Abraham Maslow's hierarchy of needs taught us that, okay? I'm sure you studied that in psychology. So you have to be convinced, if you are going to take on risk, that you have a belief that the reward is going to justify it, okay? And that's essentially what Chapter 7 is about, risk and how to measure it. And one of the techniques you're probably already aware of if you took statistics, okay? Now, I'm not much of a statistician myself, but I do know how to use some elements of stat, so don't worry, I'm not going to turn this into a stat course. You're going to find that what I show you is extremely procedural, okay? Okay, so more on that later. A refresher on layering of risk that we looked at and how an interest rate is constructed. Okay, I'll give you a quick review of that. That taught us that there are many types of risk, okay? And you have to know which ones come along with the type of investment in which you're interested. No pun intended. Okay? Generally speaking, our definition of risk here in a finance class, friends, is that it is the chance, the possibility, the measurable probability, let's say, that what actually happens might be different from what you expect. Okay? An actual outcome may differ from results that are initially expected. When you make an investment, if you're like me, and really I think this is the right way to invest, I didn't invent it, far wiser people than I will ever be invented this, you set yourself a goal. I expect that I will make this out of this investment, okay? So are you going to make it? Exactly? Well, if we all knew that, we'd all be sitting on a beach with pina coladas somewhere, okay? No, we don't. But what we can do is we can analyze the risk and hedge the bets in our favor through research and through a couple of techniques that that I will introduce you to. Again, this is a very far-reaching course of study, and my job here in this intro course is just to get you started, just to jumpstart your thinking, okay? So again, you enter an investment expecting something, let's call it a rate of return, and the possibility that you can deviate from that. Well, that's risk, isn't it? It can be on the high side, it can be on the low side, okay? But it is still a deviation from what you expect. So even though the news might be good, it is still a risk that you are taking, okay? And you want to make sure you're compensated adequately by the return that you earn for taking on that risk, okay? So we're going to look at the rate of return on the funds that we invest, okay? And how far we deviate from our expectations. There are other elements of risk that we have not talked about yet. They do not enter into our analysis of investments or in the construction of an interest rate, but they exist. Things like tax changes. The Internal Revenue Code of the United States changes every year. You have no idea what legislature will do next year, and if it affects companies or you or both adversely, well, that's an element of risk. That's an unknown, isn't it? Okay? Currency exchange rates. Currencies in the world fluctuate against each other. I wrote an article on that topic, a very simple 2-page article a few years ago, so if you'd like a copy of that, write to me, and I'll send it along. But essentially, the dollar does not stay stable against other currencies in the world, so if the dollar devalues or weakens, well, that's risk as well, okay? And even foreign assets. If a company has a foreign operation in a country whose governmental rule is subject to change, sometimes by acts of aggression, coup d'etat and such, it's not beyond reason that U.S. assets could even be seized by the new regime. Okay, so risk does come in many flavors, like Baskin-Robbins. Okay, we're going to focus here, ladies and gentlemen, on common stock. Okay, Now I want to start by defining actual rate of return. I'm going to throw away all of our rules of the time value of money just for a moment. Okay? I've talked to you about the required rate of return, the expected rate of return. The actual rate of return is just going to say, in total, regardless of the amount of time, the number of years, how much money did I make on my money? Okay? So we're going to use this a little bit in Chapter 7. So, no discounting. Okay, so the undiscounted actual percentage rate of return, think about it, on common stock. You're going to take how much capital gain you have, that's the sale price minus how much you paid for it. You're going to add to that any dividends that you received during the years in which you held that security, add all that mess together, and divide it by the purchase price, how much you originally paid. If you reason that through, you're going to say, that makes perfect sense. That's my actual percentage rate of return. Okay? To be brutally honest, there's a math error up here. If you're expressing it as a percent, you should multiply this quotient by 100. Agreed? Again, we are not discounting. This is only as to serve as a reference point. We're looking at the investment in total, ignoring discounting and ignoring time. Let's assume, for example, that you bought 100 shares of Anzavino Corporation at 50 and a quarter 3 years ago. You sell today at 62.20, and during each one of those 3 even years in which you held it, they paid you a total annual dividend of $1.32 per share. Okay, so you can analyze this in total dollars, or like times 100, or you can do it on a per share basis. Either way, the math works out. So the numerator, sale price minus purchase price, 62.20 minus 52.25. Add to that 3 years at $1.32 of dividends each, divide by how much you paid for a share, 50.25. And if you take that quotient and multiply it by 100, your undiscounted actual rate of return is 31.66%. Okay? Very simple calculation. No time value of money is considered, however. Right, the expected rate of return, okay, the ERR. I said in the first minute of this slide that I had explained it to you already. I apologize. Actually, I only up until now have covered the required rate of return. At the very end of Chapter 6, I alluded to the expected rate of return, but I did not explain it. I'm going to call it the ERR. That does not stand for error, folks. It means the expected rate of return. It might be the same as your required rate of return, but it could be substantially different. Why is that? It's because the required rate of return is, as you'll recall, a baseline. It's how much is required as a minimum by me to induce me to invest in something given its level of risk. I won't invest in that unless it pays me at least 5%. That 5% is the point at which I will decide, yes, I'll buy it. 4.8%? No, I won't. That's required. However, am I expecting it to earn me more than 5%? Yeah, who wouldn't? All right, it's going to take me 5% to put myself in the game, but I'm hoping, I'm expecting, for a variety of reasons, that this stock will actually return to me 7.5, 8%. That's the ERR, what I expect. Not what I require, what I expect. Okay? Now, that can include several variables that you consider, and that means you, in this case, in Chapter 7, we have to assign a likelihood of their occurrence. In the examples I'm going to show you, that variable is going to be what's going on with the general United States economy. Okay? I am not an economist, so what I'm going to do is I'm going to call up my friendly neighborhood economists. I'm going to go to any one of a number of econometric measurement sources, and I'm going to try to find out from the experts who really know what they're doing, what they feel the economy is going to do in the upcoming periods. They're looking at a crystal ball just like I might, but this is a little clearer than mine. So my expected rate of return is not going to be a number. No economist is going to give you a number. This will happen with certainty. No, an economist, he or she is going to give you several possible outcomes and the odds of those outcomes happening. You have to factor those into a mathematical technique that I will demonstrate for you. So I've invented 2 companies, ladies and gentlemen, Jackson and Conway. If you enjoy Mount Washington Valley as much as I do, those names will ring true for you. So I'm going to calculate, first of all, an ERR for each one of these companies. So I go out and start a massive project to table out Jackson Company's results, the return on their investment to people who invested in Jackson. I have that information in the past. Now remember, the past doesn't mean it's going to happen in the future. Okay? I'm going to look at the past. I'm going to study the past. And under different economic conditions, I'm going to call up my economist or go Google an economist and try to find out what a reasonable prediction is for how the economy will operate. So first I look at the past of the company to see how their rate of return was based on the economic conditions that existed then. Then I look into my economist, I call him or her up and say, what are the odds that the economy will be this, this, or this? And I'm going to assign likelihoods. Okay? My economist won't commit to a single number, but she'll definitely give me a bandwidth, a range. So she says to me, well, okay, I think there's a 25% chance the economy is going to be weak in the upcoming few years. 0.25 probability. Okay? Now I research my Jackson data in the past, and I see that when the economy was weak in the past, Jackson returned 5%. I multiply 0.25 by 5, and I get 1.25. You can see that I'm building a weighted average. The economist says, I believe there's a 50% chance the economy will be normal. My research shows that when the economy is normal, then Jackson gives me a 10% return. So I multiply 0.5 times 10 and I get 5. And finally, the economist says, I believe there's a 25% chance the economy will be strong. Fine, that's my weight of 0.25. And in strong years, Jackson returns 15%. Multiply it out, I get 3.75. Add those three products together, and you get a weighted average expected rate of return for Jackson of 10%. So if I analyze those probabilities, see how Jackson performs in any one of those economic backdrops or settings, multiply it out, add them up, I get 10%. I think it's reasonable to say, I'm expecting Jackson to pay me 10%. The probabilities, remember, have to add up to 100%. Okay? Otherwise, it's an invalid calculation. So when we analyze risk, our expectation is 10%. The possibility that Jackson will earn more or less than that represents risk. So it's going to be based on the weighted average. It's forward-looking plus it's back-looking. Back-looking on their actual performance under those conditions, forward-looking based on the likelihood that those conditions will exist in the future based on your economist's analysis and expectations. Friends, I want to qualify everything we're doing by saying this is called an analysis of standalone risk. Remember, this is a quick summary on this video. The chapter should be studied very, very carefully. That's where the real technique lies. I'm trying to point out the highlights, not replace what's in the book. Standalone risk means you're looking at one company or comparing one company to another. You know, as well as I do, that that's now not how I've recommended that you invest. I recommend that you invest by building a portfolio, and I'll show you why that's very important in another lecture that's forthcoming. Okay? Holding one stock is not where you want to be. You want to own several, as I'll demonstrate later. Since Jackson is the only stock we're investing, we're going to be comparing it to another company. We're measuring what we call standalone risk. When you look at a portfolio, a group of holdings, we'll have to look at it a little bit differently. All right, let me move this picture out of the way. I didn't know that was going to happen, friends, so please bear with me. Oh, there we are. We're looking at a second company, of course, as I mentioned a few minutes ago, called Conway Corporation. And we find that for the most part, the two companies are comparable. So I'm going to do the same calculation I just did for Jackson, but I'm going to do it on a different set of data. Please remember the numbers. Respectively, weak economy, normal economy, strong economy, Jackson's returns on your investment were 5%, 10%, and 15%. I forced those numbers to have a 10% expected rate of return. I'll show you why later. But those were a force. Here's Conway. Now, the same probabilities of the economy have to exist. The economy is the economy. It's the field on which both of these stocks play, so I can't go changing the probability. Those are macro numbers. However, the return for Conway in the past under those conditions has been very different from those of Jackson. When the economy is weak, our research into the past shows us that Conway has actually lost. They've had a negative impact on their return. They've lost 15%. During a normal economy, they're at 10% positive, and strong 35%. As before, multiply it out into that product column, add them together, and we get 10%. Now, again, I forced that number. I wanted Jackson and Conway to have the same ERR for a reason. Generally speaking, obviously, except for coincidence, they would not. But I'll get to that later on. That's a separate exercise. I'm going to keep it real for a moment. Which of the two companies is riskier? Now again, we defined risk as the measurable chance that an actual outcome might differ from your expected outcome. So for both of these companies, friends, what's your expected outcome? 10%. That's your ERR. We just calculated it, and it came out 10% for each. Which company, without doing any math, do you perceive as being riskier? Well, Jackson was clustered around 10%, 5, 10, or 15. Okay, so there's a little deviation there. Look at Conway. They could go much lower, and they could go much, much higher, but right in the middle is still 10%, same as Jackson. By definition, and by common sense more importantly, I think it's pretty clear that Conway is riskier. There's a greater chance that they could deviate on the downside or the upside from the 10% expected rate of return. So no math included at this point. It's intuitive to us that Conway would be the riskier of the company. You could stand to do a lot better than Jackson. You could earn as high as 35%. But, and it's a big but, if things don't go your way, you could lose 15%. Ladies and gentlemen, that's risk. Okay. Now, many of you have heard of Six Sigma, I think. Many people think that it goes back to Motorola and their quality training and all of the companies who have gone on to emulate Motorola's techniques. And you can actually, in Six Sigma formal corporate training, you can earn belts, like being a martial arts student. And I think you start at white belt, then green, then brown, then black. And now they even have master. And the more you learn about Six Sigma implementation in a company, and consequently the higher your belt, then the greater your intrinsic value to your employer and the more money you're going to make. So Six Sigma is a very worthwhile field to study. Six Sigma goes way back beyond quality studies, however. It goes back to techniques that were first isolated by a couple of scientists in the old days. I believe his first name was Francis, Sir Francis Galton, and Simeon Denis Poisson. You do not need to know those names. This is not a history course, but I find it interesting to research them. Now, how many of you had an ant farm when you were children? An ant farm. An ant farm was, as you can see in the picture on the left, it was basically two sheets of glass in a wooden frame that were very close together, and you'd fill it part of the way with dirt, and then you'd dump in a whole bunch of ants. And the ants would tunnel and create all the little underground colonies, and you could see through the sheets of glass. It was so sheer, there was such a little space that you could watch the ants as they created their colonies. You could see how their instincts operated. Then if you were a kid, every so often you might make an earthquake and shake it, okay? But that's another story. So Poisson and Galton, each independently of each other, created something like that with a whole bunch of these little pegs, as you can see, and equidistant slats in the bottom. And they would drop hundreds of marbles through, or ball bearings through a hole in the center top. And they'd bounce off the pegs as they descended, and based on their path, their trajectory, they would fall into different slats. And as you can see, the blue balls in here, also in your book, suggest that good old bell-shaped curve that we all became used to in mathematical studies. Okay? When you take a course with a dean professor, with any professor, they are expected to see a grading curve that looks just like that. A normal distribution is what we all call that. And I'm sure you've heard that term in other courses. If your professor turns in grades that do not appear to be a normal distribution, then that professor's techniques, his or her testing methods, maybe even the professor themselves, are called into question, because that is a natural process. Most natural processes will follow that so-called bell curve, that normal distribution. Okay, so that was the result of the studies of Dr. Poisson. In fact, some people call that a Poisson distribution. And if you speak French, you know that that's also the word for fish. This is more commonly known as a Galton box. I think Poisson did much more of the research, but Sir Galton's name was associated with it, so we do call it a Galton box. When you see a normal bell curve like that, it's called a normal distribution, a Poisson distribution, or a Gaussian, after Carl Friedrich Gauss, a Gaussian distribution. And it goes around what we call in mathematical studies the measure of central tendency. You learn the 3 M's, the mean, the mode, and the median, okay? We're going to focus on the mean, right in the center. That's where the hole is that the balls are being dropped through. So common sense and statistical reality would make you think that most of the balls are going to end up in the center because that's where you're dropping them. The problem is those pegs that they're bouncing off that will make some of them drift off to the sides. I think by now you all see where I'm going with this. The measure of central tendency will be the center point. We're going to use the mean, the arithmetic average for that. This is all outlined in your book. And there it is, friends. I've been leading you up to this. The standard deviation, and I'm certain that you've seen this before in stat and maybe in a psychology course you might have taken. It looks complicated, but the math and the method is quite easy. Now, Galton and Poisson determined that experiment after experiment, when they dropped thousands of these balls into these boxes, they always got a bell-shaped curve. So they rightfully said, well, it makes sense, therefore, that a natural process is going to follow a bell-shaped curve. Therefore, if we can come up with a technique that measures that curve, then that's going to allow us to measure the tendency to drift away from that center point. This is risk, isn't it? The risk that a ball will drift to the left or the right of center. And their solution was to split that curve into 6 equal increments. Each one is called a sigma, the Greek letter sigma, and that is why we call 6 sigma, 6 sigma. Okay? My time is up. I'm going to stop there, and I'll pick it up from here in my next lecture. Thank you. And today is officially the first day of the summer. Enjoy it to its fullest. See you.